Alright, so at this point, I think it would be interesting to look at the Hilbert-Bernays paradox. So I'm just going to be reading from the Wikipedia article, which for the most part just presents it in a slightly different version from this. This is sort of an abbreviated version of it, but it works. So you can actually see the things I'm saying. I wrote it out here. The Hilbert-Bernays paradox is a distinctive paradox belonging to the family of paradoxes of reference, like Berry's paradox. It is named after David Hilbert and Paul Bernays. I'm not sure if I'm pronouncing those right, but close enough. The paradox, so history, the paradox appears in Hilbert and Bernays, and this is German, so I'm definitely going to say it wrong, Grundlagen der Mathematik, something like that, and is used by them to show that a sufficiently strong consistent theory cannot contain its own reference functor. Although it has gone largely unnoticed in the course of the 20th century, it has recently been rediscovered and appreciated for the distinctive difficulties it presents. Formulation. Now this is pretty much what this is. So I'm just going to read it, but you can see more or less what's happening here. Just as the semantic property of truth seems to be governed by the naive schema T, the sentence, in quotes, P, is true if and only if P, where single quotes refers to a linguistic expression inside the quotes. The semantic property of reference seems to be governed by the naive schema R. If A exists, then the referent of A is identical with A. So I kind of abbreviated that here, but that's what that means. Right, so like the referent of A is identical, which later I started using the triple bar. Because notably that's different than the double bar equals sign. The double bar equals sign in mathematics is not an identity. It's you're not saying that these things are exactly equal to each other. In mathematics, you can get things that are non-functions. So when it's a double bar, it can be equal to multiple different things at once. Right? This is how you get things that are not functions existing. Okay. Now, let's see where we're at. Consider the name, however, a name H for natural numbers satisfying H. So consider H as the name of the natural numbers. And then this is what they have as H. H is identical with the sentence, the reference of H plus 1. I'm not sure why I have a closing parenthesis. I think I got lost. It's okay. And then for some n, 1. The reference of H is identical to n. Okay. This is a number. For some number n. Actually, more specifically, it has to be a natural number, doesn't it? Oh well. They didn't note that. Thus, or they say then surely, the reference of H exists, and so does the reference of H plus 1. Thus by R, it follows that 2, the referent of the sentence, the reference of H plus 1, is identical with the reference of H plus 1. And here I just started abbreviating referent because I got tired of writing it out. So it's just ref. And honestly, of is probably unnecessary, so like ref H would have been really nice. If I was to rewrite this, that's probably what I would do. Make it less cluttered. Anyway, 3. And so by H, and the principle of indiscernibility of identicals, I did not write that down, but I'm reading it to you. It is the case that 3, the referent of H, is identical with the referent of H plus 1. But again, by indiscernibility of identicals, and 1 and 3, we get 4. The referent of H is identical with n plus 1. And by transitivity of identity together with 1 and 4, we get 5. The result that n is identical with n plus 1. So the number is itself plus 1, according to these rules. Now, allegedly, this is absurd. as n cannot be identical to itself plus 1. Okay. The problem here is basically what I have noted with P&O arithmetic, or the P&O axioms. You don't even have to get into the arithmetic stage of it yet, because it's actually obvious that the way that the natural numbers have been defined by these rules, that you're not actually getting a unique set of numbers. You're getting a system where 2 can be 1 and 17 can be 4, and right. So you are actually producing with these logical rules, not necessarily these ones. This one is showing up the problem, but with the logical rules of the P&O axioms, that this is actually a result of what you're doing. The reason that it's seen as absurd is because of your presuppositions of how the number systems should work, and your failure to recognize how they actually work. Because if we go back over here, you can see that depending on the scale that we're using, if we're using inches, then 1 inch is the successor to 0 inches. If we're using feet, then 1 foot is the successor to 0 feet. But 1 foot is 12 inches, so 1 and 12 are each other. Two and 24 are each other. 1 yard and 3 feet are each other. 1 yard is the successor to 0 just as much as 1 foot is the successor to 0, just as much as 1 inch is the successor to 0. 0 does not have a unique successor. Under the rules of how you build out the natural numbers established by P&O, the P&O axioms, you don't get a unique 1, right? There is nowhere in those rules where this symbol was used, or some other thing which is indicating like injection or bijection or something like that. All it is the mathematical equivalence. That's all they're using, which is not powerful enough to actually prescribe this, that you only get a unique 1, and then that unit is always your unit. Thus, it's not absurd that n is looking like it's identical to n plus 1. What it is this is a problem that you never defined 1 properly in the first place. You didn't actually do the work correctly. That's where the paradox is arising from. This result, I think, is correct. I actually think this was done well. And the alleged paradox, I think, isn't one. Because if you actually understand what happened, this is what should happen. You should be getting the apparent n being identical to n plus 1. You should be getting that. And this should cause you to be very, very careful about how you talk about things. Because now, what you need to do is you need to, within your reference frame that you're working from, you need to define one very, very carefully. You need to define your unit very, very carefully so that this doesn't become a problem for you, right? We need to be looking at, well, are we talking about inches or feet or yards or millimeters or centimeters? What are we looking at? We need to be careful with our units always.